The following is my take on two related old conundrums. Here are the conundrums and analyses in question. All counting numbers are interesting, and I can prove it. First, suppose there are some uninteresting counting numbers. List them in ascending order by size. Then consider the first number in the list. It turns out that that number is quite interesting because it is the very first uninteresting counting number. Now, this is a contradiction involving the assumption that there are some uninteresting counting numbers. Therefore, all counting numbers are interesting. Not convinced? Let's pick a counting number at haphazard. Say the number 23571. Frankly, after a brief analysis, I think it seems relatively uninteresting. But I won't know for sure until I look at the numbers that precede it. Suppose I do that and find 15 uninteresting numbers. Then the first uninteresting number coming out of that analysis is still fairly interesting because is the first uninteresting number. The second uninteresting number in the list is kind of interesting, but by the time I get to the, say, 15th uninteresting number, it is still pretty uninteresting. So 23571, the 15th uninteresting number, is the first truly uninteresting number. But that's pretty interesting. I mean, it is the second first uninteresting number and the first truly uninteresting number. Anyway, we have found so far 15 interesting, uninteresting numbers. But what about the number 23572? If it is interesting, then okay. But what if it is uninteresting? Well, it is the first uninteresting number after the second first uninteresting number, so I guess it is kind of interesting. Continue this reasoning for the next, say, 15 uninteresting numbers. Then, maybe we could consider the next 14 counting numbers in our new list of uninteresting numbers interesting. But surely the 15th wouldn't be so interesting. However, in that case, the 15th number would be interesting just because it is the third first uninteresting number. But no, I don't think so. I'm getting tired of first, second, and third first uninteresting numbers. So the 15th uninteresting number is truly, truly uninteresting. But that is mildly interesting. However, after a while, uninteresting counting numbers are just, well, uninteresting. So, I submit that there are uninteresting counting numbers, although we may never be able to point to a specific one. So why were we able to prove that all counting numbers are interesting if they aren't? We were probably able to prove it because the word interesting cannot be precisely defined. That is, it is not concrete. It changes as it is applied. But more to the point, it may make sense to considering the probability that a number is interesting for the person in our proof. Let's us explore this idea more with the following conundrum. Consider the argument that a heap of sand cannot exist because if you do not have a heap already, adding an additional grain of sand will not produce a heap of sand. If you have a heap of sand and you take away one grain of sand, do you still have a heap of sand? Presumably, yes. Therefore, unless you already have a heap of sand, you cannot create it one grain at a time. And once you have a heap of sand, you cannot uncreate it by removing sand one grain at a time. Yet it is possible to have a heap of sand. It's just not possible to define exactly what it is. Here, the problem may involve an issue with the law of the excluded middle as well as the definition of heap. That is, whether I have at any moment a heap may not be either true or false, but possibly undecided, so that as I add a grain of sand, there is no single grain after which I know I have a heap. One way this could happen is if I consider the probability that I have a heap. With 1 grain of sand, the probability is 0. With 100, it is maybe 5%. With 1,000, it is maybe 20%, and so on. Where am I persuaded that I have a heap? Well, let's say I am persuaded at 80%. Although I'm persuaded, I still recognize that there is a chance that I do not have a heap. So, I continue adding grains of sand until the probability reaches 100% that I have a heap. But I can never reach 100% certainty that I have a heap of sand in this scenario. For to do so, there must be a point at which I add 1 grain of sand and find that the pile of sand has beyond doubt transitioned into a heap of sand. That is precisely what does not happen. In this scenario, I must never know beyond doubt that I have a heap of sand. Or possibly a heap transitions into something else, so that just when I think I have a heap of sand, it begins to look something like a mound of sand, for example. But how can we update our notions of the probability that a pile of sand is a heap? At this point, I'm wondering specifically about how our intuitive measurement of the probability updates. Typically, we employ a Bayesian model to update probabilities. But does Bayes or theoretical probability fit our intuitive probability mechanism? Certainty is a strange thing. I can claim that I am certain at one moment and decide at a subsequent moment that I am completely uncertain. That is, switch from 100% certainty to 0% certainty. Both difficult probabilities for the Bayesian approach to handle. Bayes will not allow me to adjust my previous estimate of certainty downward. Therefore, if my intuitive estimate of the probability of a heap is 100%, I could not later claim that is 80%, for example. Similarly, I cannot adjust my probability upward from 0%. Hence, I must never know for certain that a heap is a heap, not if my intuition is Bayesian. Yet, I can sometimes know with certainty whether a pile of sand is a heap, or whether a counting number is interesting or uninteresting to me at the moment. I can know that I do not have a heap when there is only 1 grain of sand. These considerations lead me to reject Bayesian notions as a way to update my innate probabilities about what is interesting or what is a heap. But it also makes me doubt the thesis that I am ever uncertain about whether I have a heap of sand. Is it that we are so used to uncertainty that we don't notice the uncertainty until it exceeds rather wide limits? Perhaps I do feel certain when I am only 95% certain, but it seems that I must have some innate notions about probability and an innate way of updating the probabilities. But can this update mechanism coincide with the theory of probability, or is it something different? For supposedly deterministic creatures, our thinking isn't very deterministic. It seems that change is always the order of the day. It also seems that we are quite inconsistent. Probably the best practical explanation of the conundrums is the probabilistic one, with the proviso that the person will experience periods of certainty and either degrees of uncertainty, or may vacillate between certainties. For example, that the pile of sand is a heap, and the certainty that the pile of sand is not a heap, possibly at a rate that approximates the probability of the uncertainty.